Hi, this is part 2 of the two-part video of boost converter. I tried to build the circuit I discussed in my last video. I soldered all the components in a pref board and tried to run. It didn't work. And this was because of the gate driver I used. The IR2110 gate driver IC that I used works on a minimum of 10 volt supply, and I was trying to run it on 5 volt. So I added a charge pump to generate approx 10 volt and also changed the driver IC to MC34151, which is a low side gate driver. Since here I am driving only one low side internal MOSFET, so using a low side only gate driver was a better choice for me. Then I connected again the 5 volt supply and hoped for the 12 volt output from my hyper sophisticated boost converter circuit, but it simply overloaded the PSU from where I was taking the 5 volt supply. Then I found the reason. The gate driver MC34151 actually inverts the signal. So the control system was completely malfunctioning and drawing an excessive amount of current through the inductor. So I tried to invert the PWM signal coming from the controller and gave another trial with fainted hope in my heart. But the failure record remained intact with this circuit. This time because of the BC547 BJT I was using to invert the signal. For some reason, it simply doesn't switch at this high frequency like 100 kHz. So learning from this catastrophic failure, I decided to simplify the whole design by using a peak current mode PWM controller IC UC3843. But going through the datasheet, I found that it works above 8.2 volt supply. So I came up with a very thoughtful solution. I changed the specification. Now my input voltage is 12 volt, output voltage 24 volt, and maximum output current 1 ampere. All the calculations and circuit diagram is uploaded in the Google Drive. The link is given in the description. The IC itself contains all the necessary components like error amplifier, current comparator, oscillator, and the MOSFET driver. I selected RT equals to 8.2 kΩ and CT equals to 1 nanofarad to set the switching frequency at around 200 kHz. The rest of the passive components are calculated using the equations shown in the last video, which is also given in the detailed calculation sheet, the link of which given in the description. So without wasting time, let's get into the soldering table. So the soldering is complete. Here is the ground, and this is 12 volt supply, and this is the output, supposed to be 24 volt. Here are the output capacitors, here are two electrolytics, and in the back side there is one ceramic capacitor, 10 microfarad, 10 microfarad ceramic and 10 microfarad electrolytic and 22 microfarad another electrolytic. The total is 42 microfarad. This is the main controller chip, UC3843. So you can see IRF Z44N. It's the power MOSFET. And here these parts are these two this capacitor and this resistor forms the compensator network, this 0, and this gives the feedback from the output, and this is the filtering resistor and filtering cap for the I sense, current sense, and this is the CT for the oscillator. CT and RT forms the oscillator part. This the resistor who's hiding underneath this capacitor is a 10 ohm resistor for gate supply of the power MOSFET. Coming to the back of the PCB, here is the 47 microfarad inductor, and this is a Schottky diode 1N5822, probably 3 ampere Schottky diode, and here are two 50 milliohm resistors in series, two 50 milliohm resistors connected in series, so it gives a 100 milliohm total resistor for current sensing. So the circuit is pretty much ready. Now the time to test it. To test the circuit, I'm connecting my power supply 12 volt. I'm double checking whether I'm connecting to the correct port or not. Power supply ground. This is the output. As the switching converter is not a big fan of no load condition in general, that's why I'm connecting a 100 ohm load resistor before testing. Now the moment of truth. Turning on the power supply. Okay, we are getting 21 volt output. Of course, we are supposed to get 24 volt. Why it is 21, I need to find out. But still, the boost action is happening because the input voltage is 12 volt. Let's check the 5 volt reference voltage coming out of the power management IC. It's 4.7 volt instead of 5 volt. Now I'll check the feedback voltage. It is 2.3 volt approximately instead of 2.5 volt. As per the datasheet, the feedback is compared with a 2.5 volt internal reference voltage to generate the error voltage. But it seems like the reference voltage has become somewhere near 2.3 volt. I guess they have internally used a voltage divider at 5 volt to generate 2.5 volt. Since the 5 volt reference is now 4.7 volt, so the 2.5 volt will also become 2.35 volt. Which is very close to our result. So it's a problem with the reference voltage, but overall the boost converter circuit is working perfectly fine. So that's it for this video. If you found it interesting, please like this video and consider subscribing this channel. I will be meeting in the next video. Bye.